have it in your hours, but I'll go over it again. So it's like a problem where you find the living reagent and then theoretical yield, and then from there you can see what ions are left over and how much.
Okay. Yes, we can do that. Okay. So the problem might look something like this. Hold on, I'll come up with something. Okay, ammonium sulfate aqueous plus cobalt 2 bromide aqueous. And the question, we could ask a bunch of questions about this, but a question that we could ask is, what is the theoretical yield of the solid product? Okay, that's the first question we could ask. The second question that we can ask is, what ions are present in solution when the reaction is complete? Let's start with that. Now, there's actually, I have to give you a little bit more information, because I'm just giving you the reactants. I haven't told you how much of the reactants we have. So let's suppose, well, first of all, let's make this a neutral compound. Let's make that really ammonium sulfate. But let's say we're going to combine 1.2 molar ammonium sulfate, and let's say we're going to use a half a liter of it. And then let's suppose we're going to do 0.75 molar, and we're going to do 1.5 liters of that. So that's what we're combining. So now I'm going to add a third question. And the third question is, what is final concentration of sulfate and cobalt 2 plus in solution? There are a couple chairs here, there's a couple chairs over there. All right, so that's a lot of questions. So let me just say that I cannot ask this question in this way on the exam, because it would take you too long to do it. You are all capable of doing it, but not in the 75-minute time frame, given the amount of points that I can run in this problem. But I could ask any part of this question. So I could give you part of I could get you part of the way there and ask the end part, or I could ask you the beginning part. Does that make sense? Okay. All right. So let's just start with the first question. What is the theoretical yield of the solid product? What kind of problem is this, and how do you know? Rachel.
Limiting reagent because you have numbers for two different.
Okay, so it's a limiting reagent problem. We know it's a limiting reagent problem because we have information about two different reactants. So in order to figure out what the theoretical yield is, we've got to figure out what's going to run out. Now, we have a little bit of a problem in that we haven't actually figured out what the products are yet. So why don't we stop and do that? So this is a double displacement reaction. I'm going to walk through the process of writing the products. So when I do a problem like that, like this, Now, I can do this in my head, but I don't recommend that you do it in your head, because I have a lot more experience than you do. What I recognize is what kind of ions do I have in solution, and I just write them down. I have NH4+, I have sulfate, I have cobalt 2+, and I have bromide. And notice that all I'm doing is listing what types of ions I have. I don't care how many of each I have. I'm just saying this is what's in there. And now I want to predict what are the new partnerships that could happen between the cation-anion partners. So ammonium and sulfate started off together, so I'm not going to put them together later. I'm going to put ammonium together with what else? Bromide, because I've got to put a cation with an anion. And if I'm going to put ammonium and bromide together, how many of each do I need? One of each, right? So again, I don't care how many it looks like I started with. I'm just going to say if ammonium and bromide were to come together, they have to come together in a 1-to-1. So NH4Br. What is the other product? Cobalt sulfate. So I'm going to take, so I've used this one and this one, so I'm going to take my cobalt ion, I'm going to combine it with my sulfate ion. How many of each do I need in that compound? One of each. The +2 and a -2, so I can just put one of each together. So this is a double displacement reaction. In order to be sure that a reaction is actually taking place, I need to ask, do either of these products precipitate out of solution? Are they going to be insoluble? So I'm going to have to go to my solubility rules. So they're on the second to last page of your book, if you want to open up to that page. Is ammonium bromide soluble or insoluble?
Soluble.
Soluble, because all ammonium salts are soluble. So it wouldn't even matter what bromide does. What about cobalt sulfate?
Insoluble.
Soluble or insoluble?
Insoluble.
Insoluble. How do we know? What rule are you looking at, Michael?
Rule 3, all SO4 2- salts are soluble in water. Oh wait, soluble. Yeah, soluble.
Okay. So maybe I chose something that's not going to work. I was thinking it was going to be insoluble. So sulfate salts are soluble, right? Okay. Okay. So look at this. I've just created an example that doesn't work because we need a theoretical yield of a solid product. We don't have one. Okay. So let's change this to another 2- ion. What about carbonate? What's the rule for carbonate? Is that insoluble? Okay. Sorry, I didn't mean to throw you a curveball there. I just was thinking the sulfates were insoluble. Are we done with the balanced chemical equation?
No.
No. So now, once we've predicted the products, now we have to go back and worry about how many of each we have. So I have 2 ammoniums on this side, so that must mean in order to balance it, I'm going to need a 2 here. I had 2 bromides on this side, that balances my bromides. I've got 1 cobalt and 1 carbonate, so I'm good to go. But let's just notice what I did. At the stage where I was just figuring out what the products were, I first just wrote down all my ions. So that I could say, this is what's in the mix, this is what's going to encounter each other once we mix them together. And when they encounter each other, they're going to show up in these ratios because of the charges on the ions. And then only once I've got those written down do I have to worry about how many I can balance it. Questions about that? Okay, so what's the solid product that I'm after?
Cobalt carbonate.
Cobalt carbonate. So I'm looking for cobalt carbonate. So this is the thing that I want to know. What is my theoretical yield? What is theoretical yield? By definition, what's theoretical yield? grams, so it's the grams of the product. So what I'm really asking is, how many grams of that can I get? What do we do? So we have information about 2 of our reactants. And let's change this to carbonate, so that when we get down to this, it will make sense. Okay, what do? This is a limiting reagent problem. I figured that out. I know what product I'm after.
You have to find the moles of the reactants.
Okay, so I need to know how many moles of each reactant I am starting with. So let's just start with ammonium carbonate. How do I get moles out of the information that I've got? Okay, I'm going to recognize that molarity times volume equals moles. So that's going to be 1.2 moles per liter times 0.5 liters. Just, you can do this one in my head. I don't know why I just went from my calculator. 0.6. Let's add another sig fig to this. Otherwise, we're gonna. So we have 0.6 moles of ammonium carbonate to start with. What about for our cobalt bromide? Oops. Cobalt bromide. Same thing? Okay, so molarity times volume. So I'm going to just draw a little line here. So 0.75 moles per liter times 1.5 liters. 0.75 times 1.5. I can do this one. Probably do this one later. 0.75 times 1.5. 1.125 moles of COBr2, and that's 2 sig figs. All right, so now I know how many moles of each I'm starting with. Now what?
Convert to grams.
Convert what to grams?
Your moles to grams.
So in this particular case, if I convert to grams, if I convert either of these to grams, that's going to be moving in a direction that is not going to get me to my mass of product. Because the relationship between these things and the product is in the chemical reaction that's in terms of moles. So I want to leave this in terms of moles. Going to grams is going to shoot me away from the stoichiometry rather than into the stoichiometry, if that makes any sense. So I want to use the balanced chemical equation. What do I do next?
Molar mass.
So the molar mass would do the same thing, would get me to the grams. Remind me what your name is.
Me?
Yes,
Kevin,
Kevin, thank you.
would you multiply by the molar ratio?
Okay, so now we're going to use the molar ratio from the reaction. So, and what that is going to allow us to do is answer this question. Which reactant is going to run out first? That's what we need to figure out, because the one that's going to run out first is going to determine how much product we can make. You buying that general principle in terms of figuring out what's going to run out? So I'm going to do this 2 ways. I'm going to do it the way that I showed you in class, and then I'm going to show you another way that's kind of a shortcut that will work in this particular case. What I'm going to do, and I want you to open up to page, I want you to see the scheme that we used in class. It is on page 203. So this was a basic scheme for doing the reagent problems. The examples that we were using in the book at this time were starting with mass rather than starting with molarity. So we're starting in the middle where it says moles of A and moles of B2, those boxes, that's where we're starting from. So I'm going to take the moles of each one, 0.60 moles of NH4 to CO3, and I'm going to take the 1.125 moles of COBr2, and I'm going to say, if I went all the way to product, if from either one of these, how much product could I make? So I know that it's a 1-to-1 ratio between the cobalt bromide as well as between the ammonium carbonate to get to the cobalt carbonate. With me on that? Okay. So I'm just gonna write, it's easy to do in my head, but I'm just gonna write it out. 1 mole of NH4 2 carbonate will produce 1 mole of CO3. So that means I would end up with 0.60 moles of cobalt carbonate. So this is what I would get if NH42CO3 is the limiting reagent. Right, so I'm doing the thought experiment to say, if I use all this up, this is what I can get. And as Kevin pointed out, I'm going to use the stoichiometric ratio in order to get there. So let's do the other one. I know from the balanced chemical equation that 1 mole of cobalt bromide will produce 1 mole of cobalt carbonate. If the cobalt bromide got all used up. So what's going to be my limiting reagent? The ammonium carbonate. It's going to, once we've gotten to the point where we've made 0.6 moles, we're going to have used up all the ammonium carbonate, and it doesn't matter that we could keep going with the cobalt bromide because we're done, right? We've run out of chocolate bars. We can't make any more s'mores. So that means that, therefore, NH42CO3 is the limiting reagent, which wasn't actually a question, but that could have been a question I could have asked, is what's the limiting reagent? So that means that this was a thought experiment. This is not going to happen. It's a correct calculation, but this thing isn't going to be what's happening in my beaker. What's the theoretical yield of the solid product? How do I get to that? Now I'm going to use the molar mass. Because I've got the moles of my product, now I need to get to the mass of my product. So I'm going to say 0.60 moles of cobalt carbonate will be produced, and I know that the molar mass of cobalt carbonate is, I don't know what cobalt is, so I have to look it up, 58.93. So I believe we're looking at a total mass, molar mass of 118.94 grams per mole. 71.364 grams, or 71 grams to Wright's number of sig figs. Questions about that? You all are so in week 13. It's just, I'm so sad for you, because I know how it feels. Because I'm also in week 13, but I don't have an exam, I've written it. So. Okay, so let's do a little bit of recapping. So there was an inclination, and I totally understand it, to, when you see moles, say, oh, let's go to grams. But when it's a limiting reagent problem, if you're at moles, your next step is to figure out what runs out first, and you move towards products first. Okay? So we move to products by using our stoichiometric coefficients, And in this case, the way we solved that problem was to figure out, use both of them, go all the way to the product, figure out what was gonna produce the least of it, and then go to grams. So I said I was gonna show you another way to do it. If we had just paused here and noticed that this is what we were starting with, what's the ratio between those two reactants? 1 to 1. Which one's gonna run out first? The 0.6 is gonna run out first. As soon as we're done with this, we can't use all this up because it's a 1 to 1 ratio. So in other words, if I have 0.6 moles of this, that means I need 0.6 moles of this one, and I got more than 0.6. So that means right from here, given this is a 1 to 1, I can eyeball this and say this is the limiting reagent. Just by looking at it. Now, I still have to do this calculation to get to here. So it doesn't save you a lot, but if you can look at it and eyeball it at that stage, that's also a fine way to identify what the limiting reagent is. Okay? Kevin?
So if you're just given grams first instead of like the molarity and the liters, would you just convert to moles and then do the same thing?
Exactly. So if you had a problem where the two reactants were given in terms of grams, your first step would be to convert to moles. You'd be at a place where it was similar to this, and then you would do this. Next step, absolutely. Yep. And you could have something where one reactant is in grams and another reactant is in moles in volume, right? And so then you get both of them to moles, and then you do this kind of thing. Right? The idea is, with the limiting reagent problems, you have to figure out which reactant is going to run out first, and you have to get them both to moles in order to start to ask that question. Scott?
I saw an example where it said what your yield was, and then you had to figure out if it was a limiting
Yes.
reactant.
So let's imagine that the question was not what is the theoretical yield, but if I said the theoretical yield is 71 grams, your actual yield, let me get back to my black marker, I'm trying to use black because it shows up in the video better. If your actual yield is 35.2 grams, what is the percent yield? So percent is always part over the whole times 1,000, so not 100. So this is the part of what this is the whole thing. You expected 71 grams, that's the whole thing. You only got part of it. And that happens all the time in real reactions, that when you combine things, you don't get exactly what you would have expected, because not all the reactants react, or you lose something when you spill it on the counter, or whatever. It happens all the time. So the percent yield will be the part over the whole, which will be the actual over theoretical, times 100. So in this case, it will be 35.2 grams over 71 grams, and whatever that comes out, times 100, 49.5. And since we're limited to 2 sig figs, we would round to 50 grams. Okay. Now, everybody take a big deep breath. We're at 8:13, and you're all like, right? And we've only just answered the first question. But you're all good, right? Big deep breath. All right. We now know, so because we've done a lot here, we predicted what the solid product was. We've identified what the limiting reagent was. And now we've predicted the theoretical yield of the solid product. Now, I love this question. There's a question like this on last year's exam. If anybody's looked at last year's exam yet, there's a question that's a lot like this, or at least a piece of this. The question is, what ions are present when the reaction is complete? So let's go back and remind ourselves what was in there. So we said that when we started, we had ammonium in there, we in there, we had cobalt in there, and we had bromide in there. I want you to spend a minute talking to someone next to you, seeing if you can figure out what do you think is left in, what ions are there. Are they all still in there? Are only some of them in there? What's left in solution? So in other words, what's aqueous? What are the ions that are aqueous?
Hi. Hold over a second. That's just there was no one in that. Emptied out about a half hour later. And then when the last person was 15 minutes before we closed, well, we're not really supposed to let anyone in. We're not really supposed to let anyone in. Like 15 minutes before we close.
Okay, what's in there? So let me, we'll do one at a
Just go
time.
in and just leave it.
Are there ammonium ions still in solution? Yes. And how do we know that there's ammonium ions still in solution? Because we can see in the product that these are going to be our spectator ions. So once you get those ammonium ions dissolved, they're just going to hang out in solution. Doesn't matter what else is happening, right? So yes, we have ammonium ions in solution. Do we have carbonate left in solution? No. Why not? Okay, we see it in the solid. Okay. All right, so I'm going to write no here, but I'm going to come back to the reason in a minute. Are there cobalt ions in solution? Okay. Yeah, I'm going to come back to this because I want us to re-examine that. So let's go to bromide. Is there bromide left in solution?
Yeah.
Yeah. How do we know? It's aqueous. It's a spectator ion. So no matter what you do, whatever else is going on, it's going to be dissolved in solution. So yes, that's going to be in solution. Now, I want to go back to this idea about the cobalt and the carbonate. Because it is absolutely the case that the balanced chemical equation tells you that they are going to be in the solid. But let's remember that this was our limiting reagent. Which means this is not the limiting reagent. We're not going to run out of this. We're going to run out of this. So all the carbonate will end up here. We're going to react all 0.6 moles of that. So I would agree that the carbonate is not in solution at the end. But the cobalt is part of a sample. Remember, we had more moles of cobalt bromide than we needed. So there's some of it is going to end up in this solid, and some of it's just going to be left over. So there is going to be cobalt ions left in solution. I love that question because you have to picture what's going on. It's a limiting reagent problem. It's so awesome. I can understand why you might not love it, but I love it. Okay, so now we know what ions are present in solution. Everything but the carbonate is still in their solution. So then what is the final concentration of carbonate and cobalt in solution? So what is the final concentration of carbonate in solution? 0, right? It isn't in solution anymore. It's been precipitated out. So the carbonate will be 0. Molar. Now, the cobalt in solution is a tricky problem to solve. You have the skills to do it, but let's figure out what's going on. So I'm going to create myself some space. So to figure out the concentration of cobalt, we need to know 3 things. We need to know the number of moles of cobalt when we started. We need to know the number of moles of cobalt that reacted to form CO3. need to know the total volume? Now, why do we need to know those things? If we know how many moles we started with, and we know how many moles reacted, we can subtract one from the other to get how many moles were left over, and then we just divide it by the volume to get the molarity. That make sense? So do we know how many moles of cobalt we started with?
Yes.
Yeah. So we know that we started with 1.125 moles of cobalt 2+. Now notice that I'm making a leap here. This was moles of cobalt bromide, but I know that there's one cobalt in every cobalt bromide, so I'm gonna just treat it as though the bromides have dissociated away, they're hanging out in solution. So I know that this number of moles is moles of cobalt in solution when we started. What's the total volume?
2 liters.
2 liters. So we took our two things together, so our total volume is 2 liters. So what we have left to figure out is how many moles reacted. What was our limiting reagent? Ammonium carbonate. By definition, this is our limiting reagent, that means all of it reacted. So if 0.6 moles of ammonium carbonate reacted, how many moles of cobalt bromide reacted? 0.6, because it's 1 to 1. If it wasn't 1 to 1, we'd have to use a stoichiometric ratio to figure out, like maybe it's 2 to 1 or whatever. But the number of moles of cobalt that reacted is going to be 0.60 moles of cobalt. Because it's 1 to 1. And because there's one cobalt in that compound. So then, to get the molarity, I'm going to say moles left is equal to what we started with, 1.125 moles of cobalt, minus what reacted, 0.60 moles of cobalt. And that is, what did I do from things here? 1.125 minus 0.6 equals 0.525 moles of cobalt left. Then the molarity will be 0.525 moles of cobalt divided by my 2 liters. 0.26 molar cobalt. Everybody breathe. So recognize, I cannot ask you, it just took us a half an hour to do that problem, right? And I was explaining along the way, right? I could do that problem on my own more quickly, but I do not expect that you would be able to do this problem start to finish during an normal exam. If I gave it to you as a take-home problem, I might expect you to bang your head against the wall for a while, right? But I could ask you any piece of this, right? I could give you enough information for you to just calculate the final concentration of what's left over. I could ask you to predict the products. I could give you information and just have you get to the theoretical yield, etc. So I could give you enough pieces that you wouldn't have to do the whole thing, but you could do any one of those pieces. Hold on just a second, I'm going to stop the video and start it so that I've got smaller chunks to try to upload. And then I can take another question.